Acid-base titration, example number 2. Answer the following questions regarding a 0.05 liter solution of a 0.1 molar solution of a weak acid, symbolized HA. Given the acid dissociation constant, known as 4.5 times 10 to the negative 6, the solution is titrated with 0.1 molar sodium hydroxide, and the pH at the equivalence point is given to us approximately to be 9.2. Part A, calculate the volume of the base needed to reach the equivalence point. Part B, calculate the pKa for the weak acid. Part C, determine the pH of the original acid solution before titration begins. Part D, sketch a titration curve. We know the volume and molarity of a weak acid. We know its dissociation constant. We know the molarity of the strong base being used to titrate it, sodium hydroxide, and we're given the pH at equivalence point in the basic range of 9.2. Let's knock it out. Start by calculating the number of moles of acid that are in that original solution. We can do that by knowing that molarity times volume gives us the number of moles. Notice here that liters cancel out and give us a number of moles. And dealing with the stoichiometry, we know that this weak acid is monoproctic, so it reacts with the sodium hydroxide in a 1-to-1 ratio. So we're going to need 0.005 moles of sodium hydroxide to reach the equivalence point. From then, we need to know what the question actually asked for, which was not number of moles, it was the volume. So we're going to use the relationship that says volume equals the number of moles divided by the molarity. In this case, 0.005 moles divided by 0.1 moles per liter of molarity. Notice that the moles cancel out. We will report that with 3 significant figures of confidence. Clear, simple, and done. Now, part B. Part B says find the pKa for that weak acid. Let's find the pKa from the given dissociation constant, K sub A. Note here that larger dissociation constants, K sub A, equate to stronger acids. And conversely to that, smaller pKa values relate to stronger acids. What the heck is a pKa in the first place? Well, it's simply taking the negative log of the dissociation constant value. Note here that the P stands for power from the German word potens, calculator. We know the acid dissociation constant is 4.5, 10 to the negative 6. Take the negative log of that value. The most difficult thing here is just being confident with your calculator and that you know how to put it in. pKa comes out to 5.35. We're going to hold on to that value because later on we're going to use it to graph our half equivalence point where we know that there's 50 milliliters of base that has been added and the pH will be at 5.35. So part A, done. Part B, done. Part C, determine the pH of the original acid solution. We know the concentration of the weak acid and we know its dissociation constant. Here is our dissociation equation. Here is our Rice table, initial concentration, the shift or change that occurs to reach an equilibrium, and quick point here that we're calling this an initial concentration, but that's at the inaugural mixing. I think I'd prefer to, instead of calling this a Rice table with initial change equilibrium, I'd rather call it inaugural mixing, because once we mix our acid into our water, it's going to shift towards an equilibrium. And then we're going to treat it with a titration. So the word initial here could be confusing. Initial here resulting in a change, and then a new situation, which we're going to call the initial situation later on during the full titration. So instead of calling this initial concentration, I'm going to call it the inaugural or first mixing concentration. Again, we know the case of A. We know that initial concentration of the weak acid, before any shift towards equilibrium occurs, there is no hydroniums and no conjugate. Once that shift occurs, we will have X values of the hydronium, we will have X values of the conjugate base, and we will have a shift from this original concentration. But this case is usually considered to be less than 5% strong, which means it is often ignored. All right, so the case of A, acid dissociation constant, isn't the X value, but we're going to use it to find the X value with our dissociation constant setup equation here. All right, so the hydroniums and the conjugate both shift by X, and the original acid will be reduced by X. If this X value is so small that it's not going to influence this with a reasonable amount, we can ignore it and simplify it down to X squared over 0.1. Now, solving for case of A here, or essentially multiplying the 0.1 times the case of A equals X squared. Taking the square root gives us 6.71 times 10 to the 4th moles per liter. Okay, so that is how far these values shift. If the acid, or if the hydronium, hydrogen concentration shifted from 0 to this, well, the pH will simply be the negative log of that concentration, right? We'll plug it into the calculator, it gives us a pH of 3.7. Shortcut alert. We could have looked at this a different way. If you want a faster path on the exam, we could say that the pH equals about about 1/2 the negative log of the dissociation constant minus the log of the concentration of acids. Essentially, we're taking this value here, taking the negative log of both parts, knowing that since these are products, these need to be added, and it gives us this version of the formula. Does this work? Do we have those values? We do. We have a acid dissociation constant, and we have a concentration of acids. So we can plug those in, and the calculator gives us 3.17, which agrees with the other route. This shortcut gets the same place with a little less algebra. Definitely maybe want to keep that in your toolkit. We've done part A, we've done part B, and now we just knocked out part C. Part D, sketch our titration curve. Our initial point, when there's 0 sodium hydroxide added, we had an initial pH of 3.17. I'm going to draw a little line there to show that that will trend upwards as the sodium hydroxide is added. The pH will increase, less acidic, more basic. At half equivalence point, we learned that that took 25 milliliters of sodium hydroxide to reach that, because it was half of the 50 to reach a full equivalence. So half equivalence would be half that value, and we also know the pH at that value. Half equivalent or full equivalence was reached at 50 milliliters at a pH of 9.2. For the half equivalence, I'm going to put a near horizontal line, and for the equivalence point, I'm going to put a near vertical change, okay, and add my curve. This curve approaches 12, so it's going to level out above 11 and near 12. That's all I needed to sketch, a clean S-shaped titration curve. emphasize those three critical anchors are really the important part. The initial pH, the half equivalence pH, which is also equal to the pKa, and the sharp jump at equivalence. We know the pattern, and we should trust the process. So we knocked out A, B, C, and we sketched a decent titration curve. We calculated what we needed to. We converted Kas to pKa. We solved the initial pH using equilibrium principles. We graphed the titration curve. This question brought together all those key concepts, and we did it. Solid work. Heck yeah. All right, scratch this down on paper at least twice, because you need to hang one by your bed so you look at it every night before you go to bed, and tape one on your bathroom sink so you can take a look at it and think about it while you brush your teeth.